Magnets are all around us, from the simplest child's toy to the most powerful electromagnet. Even the Earth acts as a giant magnet. Its magnetic field is responsible for the phenomenon known as the Northern Lights. And the discovery of the link between electricity and magnetism has led to inventions such as the generator and the electric motor. A telephone is an example of a device containing both a generator and a motor, one in the mouthpiece and the other in the earpiece. During this unit on magnetism and electromagnetism, we will explore magnetic forces, their causes, effects, and their many uses in our lives.
During this lesson, you will describe the properties of magnets and compasses and explain the origins of magnetic properties in materials at the atomic level. Finally, you will define domains and describe how they align themselves in a magnetic field.
Welcome to the mysterious world of Magnetoman! But my world won't be so mysterious to you after we finish our study of magnetism. See all these things that are attracted to me? That's because of my superpowers. But enough about me. Ha 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 ha. Let's start our study of magnetism with something far less exciting. Let's look at some properties of a simple bar magnet like this one. Now, you've all seen a bar magnet before, and you know that it has two poles, one north and the other south. And I'm sure you know some simple facts about how these poles interact. But let's go over them again just to be sure. We'll start in the lab.
A bar magnet is placed in a holder that is suspended from a string. This allows the magnet to move freely. When the north pole of a second magnet is brought close to the north pole of this magnet, it turns away. Like poles of magnets repel. The north pole of one magnet will repel the north pole of another magnet. The same is true of two south poles. Next, the south pole of the second magnet is brought close to the north pole of the suspended magnet. This time, they attract. Unlike magnetic poles attract, north attracts south. Notice that the forces of attraction and repulsion do not require that the objects touch. Magnetic forces are field forces. A magnetic field is the space around a magnet in which a magnetic force of attraction or repulsion is exerted. You will learn how to draw magnetic fields in the next program.
Okay, we've established the fact that the north pole of one magnet will attract the south pole of another magnet. But have you ever wondered why we call these poles north and south? Well, it all started with a rock like this one. Over 2,000 years ago, the early Greeks discovered a magnetic ore in a region of Turkey called Magnesia. That's where the term magnetism came from. And somehow, in the 12th century, the Chinese found that when a single stone made of this ore was suspended, one end always turned toward geographical north. These natural magnets, called lodestones or leading stones, were used to navigate ships. So the Chinese invented the first compass. A compass is just a magnet that is free to move, like this one. Now do you see where the north pole of a magnet got its name? Better get some notes on all this.
The north pole of a magnet, abbreviated with a capital N, means north-seeking because it seeks geographic north. The south pole means south-seeking because it seeks geographic south. A compass is a magnet that is suspended in some way so it is free to move. A compass needle moves to align itself with the Earth's magnetic field.
Now, you physics types out there should be really bothered by a couple of contradictory statements you've just heard, and you've even put into your notes. Your teacher will pause the tape so that you can take a minute and look back over your notes to find the two statements that contradict each other. Come back after you've discussed it in class.
The two statements that seem to contradict are these: like magnetic poles repel, and the north pole is the north-seeking pole. Seeks means is attracted to, so it seems that north attracts north. Shouldn't north be repelled by north? Yes, and here's the explanation. The Earth acts like a giant magnet. We'll learn why later. And the magnetic needle of a compass is affected by the Earth's magnetic field. So if the north pole of a compass magnet aligns itself with geographic north, which pole of the Earth's magnet is located near geographic north? Tell your teacher. It's the south magnetic pole, of course. The south pole of the Earth's magnetic field is located close to geographic north. So, the north pole of a compass magnet is attracted to this south magnetic pole. Opposite magnetic poles still attract. The confusion comes in using the words north and south to describe both geographic and magnetic poles, which are two entirely different things. So, go back to your notes and add the word geographic to the north-seeking pole, like this.
Here's a physics fact or fiction challenge for you. On a foggy night, Santa Claus can use a compass to find his way home to the North Pole.
This one is fiction. A compass would lead Santa to the Earth's south magnetic pole, located in Hudson Bay, Canada, about 1,200 kilometers south of Santa's home at the North Geographic Pole. On a foggy night, Santa would be better off using Rudolph to guide his sleigh. At any location on the surface of the Earth, the difference between the magnetic and geographic poles is called the magnetic declination. For example, along a line through South Carolina and the Great Lakes, a compass magnet will point to geographic north. But in Los Angeles, it will point 15 degrees east of geographic north. So its declination is 15 degrees east. Okay, now that you know how the poles of a magnet got their names and how compasses work, let's answer some more magnetic questions. We'll start with this one. Why are these washers attracted to a magnet and these aren't? What kinds of materials are magnetic anyway? Sounds like a good lab investigation. Your teacher will give you this data table from Unit 10 of the Facilitator's Guide. When you're ready to make your observations, come back and we'll go to the lab.
Materials are classified as magnetic if they are attracted to a magnet. Our students will test each object to see if it contains a magnetic material. On your data table, place a check by the objects that are attracted to the magnet.
Well, I checked off 4 objects that were attracted to the magnet. We classify the materials composing these objects as magnetic. Now you need to decide what the 4 materials have in common. Talk it over and come back when you've made your conclusion. What do the paperclip, nail, razor blade, and straight pin have in common? If you said that they are all metals, well, you're surfing. You didn't notice that the aluminum foil, zinc, quarter, and penny were not magnetic, and they're all metals. Now, you have to look a little deeper. Did you notice that all of the objects have iron in them? That's the common link. Iron is a magnetic material.
We call elements strongly attracted to a magnet ferromagnetic. Save room for more notes on ferromagnetic elements. But first, think back to chemistry and see if you can remember where the term ferromagnetic comes from. Tell your teacher. The symbol for iron is Fe, and it comes from the Latin name for iron, ferrum.
Now, what causes the magnet to attract iron and other ferromagnetic elements? To answer this, we have to look at the electron structure of the atom. Put your pencils down as we review a little chemistry. I'll tell you when to take notes. This is the first of many times that we'll talk about the link between electrons in motion and magnetism. The fact is that moving charged particles, like electrons, produce magnetic fields. And it's the spinning movement of electrons within the atom that is responsible for the atom's magnetic properties. An electron spins on its axis, producing a magnetic field. If it spins in one direction, the south pole will be on top and the north pole on bottom, like this. And if it spins in the opposite direction, the poles will be reversed, like this. In atoms containing many electrons, most of the electrons will pair up, like this, with their spins opposite each other, producing magnetic fields that cancel each other out. However, in ferromagnetic metals, like iron, many of the electrons remain unpaired, like this, spinning in the same direction and giving the atoms magnetic properties. Now it's time to pick your pencils up and take some notes.
Let's add to your notes on ferromagnetic elements. You've already written that ferromagnetic elements are strongly attracted to magnets. Why? Because these elements have many unpaired electrons spinning in the same direction that produce identical magnetic fields. Iron, nickel, and cobalt are the most common ferromagnetic elements. They have atomic numbers of 26, 27, and 28, and are adjacent on the periodic table, so they are easy to remember.
Many students make the mistake of treating magnetic poles like electric charges, saying things like, the ends of a magnet have opposite charges. Remember that the iron and other elements in this magnet are made up of neutral atoms. There are no charges, just magnetic poles. And there's another big difference between electric charges and magnetic poles. You can have a negatively charged object without a positive one, but there is no such thing as a monopole. Even the smallest magnetic particle, a spinning electron, has both a north pole and a south pole. You can't have one without the other. These ring magnets illustrate my point. Their shape may fool you, but each one has a north and a south pole. Let me show you what I mean. You can see that these magnets attract. But let me place them on a stand, dropping one on top of the other. This one repels so strongly that it defies gravity. So the tops and bottoms of ring magnets have opposite poles. Oh, I almost forgot another question for you. If magnets are made of iron and nails are made of iron, why aren't all nails magnets? Good question, huh? Let's go to the lab and do some investigating.
Let's see if our students can turn a nail into a magnet. A nail is placed on one pole of a bar magnet. It attracts. Next, another nail is put at the end of the first nail. It attracts too. This is continued until the last nail won't hold. Now the magnet is removed. Some of the nails are still attracted. So our nails have become magnets. But watch what happens when the nails are dropped on the table and our student tries to use one to hold up another. It's obvious that any magnetic polarization the nails obtained is only temporary.
So why aren't all nails magnets? And how does one become a magnet? It can all be explained with a new physics term, domains. Domains are large groups of neighboring ferromagnetic atoms whose magnetic fields are aligned, making the group act like a microscopic magnet. In an unmagnetized substance, like a nail, the domains are randomly oriented, so the nail does not act like a magnet. But when the substance is brought into an external magnetic field, the domains align, giving the substance a north and south pole. This is called magnetic induction. The process is similar to the induction of a static charge, but it can be accomplished with or without touching, as you will see later.
Let's look at magnetic induction more closely. This diagram roughly represents a piece of iron like a nail. Because the iron is ferromagnetic, it has domains. These small magnets represent the domains, which are randomly aligned. Now, when the iron is brought into a magnetic field, such as the one around the north pole of this bar magnet, the domains begin to respond to the field and are induced into moving around like this, with south poles being attracted to the north pole of the magnet. Finally, the domains are aligned like this. The nail now has a north pole and a south pole. It has become a temporary magnet with its own magnetic field. It can now attract another nail. But when the external magnetic field is removed, the domains will go back to their random pattern due to the natural random motion of atoms.
Have you ever played with this toy? I'm using a magnet to drag around tiny pieces of iron, called iron filings. We can use these iron filings to represent the domains in a ferromagnetic substance. Watch this demonstration.
Let's use a test tube filled with iron filings to represent the domain inside a piece of iron. Shaking the tube makes the filings fall in a random arrangement. When we pass a compass needle close to this random arrangement of filings, the needle is not affected, so the tube of filings does not act like a magnet. Place a tube of filings on top of a bar magnet and gently shake both to give the filings a chance to react to the magnetic field of the bar magnet. Each small piece of iron can turn around like the domains of atoms inside the nail can turn. Notice how the filings line up, especially around the poles of the magnet. Next, we'll remove the magnet, being careful not to disturb the arrangement of the filings. This time, when we bring the compass needle close, it is attracted and repelled by the different ends of the tube. We have created a magnet out of iron filings, just as a nail can become a magnet due to the movement of its domain.
Just like the iron filings in this tube are all mixed up now. Dropping a nail, after it has become magnetized, jostles its domains out of alignment also. Dropping a permanent magnet weakens it, but it's not as easy to make a permanent magnet lose its polarity. Why? Well, it has to do with the type of material it is made of. Iron is considered to be a soft magnetic material because its domains can slip into and out of alignment easily. Soft iron does not make a good permanent magnet for this reason. But hard magnetic materials, like steel or other alloys, are harder to magnetize because their domains don't turn as easily. However, once the domains are aligned, the alignment persists after the external magnetic field is removed. These hard metals make good permanent magnets. This razor blade is made of stainless steel, an alloy, so the material is harder than pure iron alone. The domains inside the blade cannot turn easily in response to a magnetic field. We'll need to use another method of magnetic induction than merely bringing it close to a magnet. This time, the process of induction will involve touching the object. Watch.
First, the north pole of a bar magnet is used to stroke the razor blade, starting in the middle and moving toward the top end. Next, the south pole of the magnet is used to stroke the same blade from the middle to the bottom end. Let's see how the razor blade has been affected. We'll place the blade on the surface of a dish of water so that the surface tension of the water will hold it up. No matter which direction we turn the razor blade, it always returns to the same direction, with the top of the blade pointing toward geographic north. We've turned the blade into a magnet, and by making it free to move, we've made it a compass. Watch what happens when we bring a magnet close. Our razor blade responds the same way any compass magnet would, reacting to the stronger magnetic field. How do you think a magnet would be affected by breaking it in two? Tell your teacher. Let's try this with our homemade magnet. We'll snap the razor blade in half and place the halves back in the water. The halves attract each other and return to the original alignment.
Breaking a magnet in half just makes two magnets. Did you predict that? Look at this diagram of the domains in a permanent magnet. Breaking the magnet in two does not affect the alignment of the domains. So, dropping or hitting a permanent magnet will weaken or destroy it, but breaking it into pieces will not affect it. What do you think about heating a magnet? Will that weaken it? Tell your teacher. I'll wait. Heating will weaken a magnet. Heating increases the thermal random motion of the atoms, making the domains lose some of their alignment. It's like shaking this tube of iron filings, which made it lose its polarity. Well, you've learned a lot about magnets today, so it's time to show